Yes. So the abstract I sent is about graphical designs, which the students in this course have already seen, but I'm going to do a summary of graphical design. So hopefully it's bearable for the students. And then in the second half of the lecture, I'm going to present new results even to the students about some recent results we have about these designs, okay? So there are, I'm going to try to do this on the board. There are some slides with pictures, so if we have time later, we can look at some of the pictures. But I want to do a pretty efficient summary on the board, okay? So let's try. Okay, so the topic is graphical designs. And yeah, let's keep it there. And this is joint work with several people. So my main collaborator is Stefan Steinerberger. Who is my colleague at the University of Washington. He's a harmonic analyst and many other things. He's very, very broad. He's an analyst, that's the point. And then there are further papers with students. So there is a student of mine who's done quite a bit of work on it, whose name is Catherine Babecki. So she established some of the very basic results about designs. She's at Caltech. And then a current student who is Zawad Chowdhury. Okay, so I'll just mention those names for now, and then if anything else comes up, I will let you know. Okay, so it's joint, it's a collection of papers with all of these people. Okay, so what's the question? So let me first tell you what a graphical design is. So I start with a graph. Let's assume that its vertex set is just the set 1 through n. So that's the combinatorics notation for that, the set 1 through n. And then we have some edge set. Let's call it E, okay? So I will assume that this graph is really, really nice. Actually, yeah, let me just go ahead and call this V. So this is the vertex set, this is the edge set. And we'll assume that this graph is as nice as you want, okay? So it's finite, it's connected, it's undirected, it's unweighted. Very nice, okay? No complications with this graph. So simple, exactly. So it's going to be simple, that means no loops, no multiple edges. It's going to be connected. It's going to be unweighted and undirected, etc. Okay? So that's what this graph is. Okay. Now, associated to graphs, there are many, many types of matrices. For today, let's focus on the Laplacian. Okay? So a graph has a matrix associated to it called its Laplacian. So this we will denote by L. And what this is the difference of two matrices. So the first matrix is just the diagonal matrix. So let me write it like this first. So it's written like this, D minus A, where D is the diagonal matrix where you put the degrees of the vertices on the diagonal. Okay, so this is the degree of vertex V1 all the way up to the degree of vertex Vn. Okay, so by degree I mean the number of edges touching that vertex. So it's a diagonal matrix like this, that's D. And this A is the adjacency matrix of the graph. So this one is the adjacency matrix. So that's just recording the edges in the graph. So its definition is that Aij will be equal to 1 if Ij is an edge, and it's equal to 0 otherwise. Okay? So it's a symmetric matrix, and it will have zeros on the diagonal because I don't have any loops in my graph. So it has zeros on the diagonal, but it's symmetric with zeros and ones. Otherwise, this is the diagonal, this is the degree matrix. Okay, so if you want a very simple example, let's do a simple example. Maybe we take just a triangle. So the vertices are, let's say, just 1, 2, 3, instead of calling it V1, V2, V3. So then in this example, let's actually make it a little bit more interesting. Let's also have another vertex 4. So then I have the matrix, this matrix L is a V by V matrix. So it's indexed by the vertices of the graph. And in the diagonal, we put the degrees of the vertices, okay? And this one has nothing in the diagonal, zeros in the diagonal, so I can just go ahead and put the degrees down. So degree of vertex 1 is 3, that's fine. Degree of vertex 2 is 2. Degree of vertex 3 is 2. And degree of vertex 4 is 1. So those are the degrees, okay? And in the off diagonal, I have to put a 1 every time, I have to put a minus 1 because I'm subtracting this every time there's an edge in that position, okay? So for example, 1, 2 is an edge, so I put this here. 1 is in fact connected to everything, so I have to put minus 1s everywhere. And then by symmetry, this also happens, right? If ij is an edge, then ji is also an edge. It's not a directed graph, so we have this, okay? And then what else is left? So 2 is connected to 3 and 1, so it's already connected to 1, so I connect it to 3, and then we do that. 2 is not connected to 4. And then 3 is connected to 1 and 2, which we already got, right? Yeah, 3 we already got, so it's that, and then we're done, right? 4 is just connected to 1. So this is the Laplacian, okay? So it's kind of a finite analog of the Laplace operator on a continuous object, but this for the graphs, this is a nice matrix, okay? So what are some properties of this matrix? So the key property that we're going to exploit is that this is a positive semi-definite matrix, okay? So that means all its eigenvalues are greater or equal to 0. That's one definition. So that's good. And hopefully you can immediately see that if I multiply on the right with the all ones vector, then I get 0. Do you agree? Because in the diagonal sits the degree of the vertex, and in the row of that entry in a particular row, you have minus 1s for every edge that's touching that edge. So this product is going to give us 0, okay? So this is the 0 vector. So this immediately tells you that 0 is an eigenvalue, right, with eigenvector 1, 1, 1, 1, 1. Good. So because of the PSD, I know that the top eigenvalue, whatever it is, has to be non-negative, but it's actually 0, right? We just proved that 0 is an eigenvalue with eigenvector 1, 1, 1, 1, 1. Okay, and then the other eigenvalues have to be greater equal because of the PSD condition. This is an n by n matrix that's symmetric, so all the eigenvalues are real, they are non-negative, they can be ordered. The first one is 0. Everybody okay? All right, so this is the Laplacian, okay? And there are lots of nice, okay, so that's the first thing. This is what we can say about the eigenvalues. And then because it's a symmetric matrix, this also has a full orthonormal set of eigenvectors, right? So let's denote the eigenvectors by phi. So phi1, which we just saw, is a scaling of 1, if you want. And then it has phi2 all the way up to phi n. These are the eigenvectors. And we can assume this is an orthonormal set. Okay, if you want, you can just take it to be orthogonal. For different purposes, we need to do different things. But it's a full eigenbasis. It actually is a function, a basis for all of space. Okay, so that is the setup that we're going to work with. And now, suppose we want to do something like this, right? Suppose we have a function f on the graph, a real valued function on the graph. So that means I'm putting a number on top of every vertex, okay? And I'm interested in calculating the global average of this function on the entire graph. So think of a massive graph with millions of vertices. I have a function that's sitting on top of it. For example, I could have rainfall, average rainfall in every single place that Google Maps will locate in the state of Karnataka. Okay, that's a lot of places. And let's say we connect things together if there are roads between those places or something like that. Okay, so I have a function like this, and this is because we have a basis for all of space. I know that this is a linear combination of all the phi's from 1 to n, right? Because it's just some function, and we had that. Okay. Now, here's a fact that I hopefully convince the students. that if your function is sufficiently smooth on the graph, which means that when you move from a vertex to an adjacent vertex, the function value doesn't change too much. If that happens, then this function is actually in the span of the first few eigenvectors, okay? So these eigenvectors are sort of like, you can think of them like a Fourier basis. So the first one, which is all ones, what is it doing? It's just putting value 1 on every vertex. So it's moving extremely smoothly from one vertex to the next one, right? There's no change. It's just constant, sorry. Keep breaking these chalks. Okay, so this one is really nice. And then the next one, when you go over, it's going to have different numbers. It's going to have plus and minus numbers. But when you go from one edge to one vertex to an adjacent edge, the variation is going to be small, okay? So we can see a picture at the end of the talk, because I think this is quite nice. So as you increase the value of lambda, these phi's are going to be they're going to vary more and more. They're going to be less and less smooth, okay, on the graph. And the very top eigenvectors are going to be very, very oscillatory. So just like in a Fourier basis, the first wave is really smooth, sine theta, cosine theta. The next one is a little bit more oscillatory. The next one is even more oscillatory. And by the end, it's very, very, very oscillatory, right? So if I just want to capture a smooth function in Fourier analysis, we don't need to take all the basis vectors. We can just take the first few waves, and your function is a combination of those, right? Similarly, if your function is sufficiently smooth here, we can assume that f is in the span of the first. So f smooth, sufficiently smooth, let's say, implies that I can write f as a combination of just the first, let's say, k eigenfunctions, okay? So at the end of the talk, I'll show you a picture of how these eigenvectors vary, and this is something that's very nice. And this basically comes from looking at the Rayleigh quotient, Courant-Fisher, whatever you like, okay? There are different ways to convince yourself of this fact, but maybe picture is the most convincing, so I will show you something at the end, okay? So we can fire up the projector just once. Okay. So I have a function like this. So think of rainfall function, think of like medical data, maybe we're measuring blood pressure of everybody in the city of Bangalore. They're connected by some kind of family relationship, genetic relationship, I don't know, whatever you want, okay? And then, so it's probably going to be fairly smooth if, you know, from edge to edge, right? Like if you, okay, we have to control the population for that example. So let's just take students from the age of 20 to 25 in this institution and connect them by whatever you want to connect them by. It has to be something reasonable. We expect some sort of smooth function, and I'm interested in calculating the global average of this function on the graph, okay? So this is what I want to do. Okay, so a graphical design is going to be a subset of the vertices of my graph that's going to do the averaging for you, okay? So you don't need to actually count every single person's data. We're just going to cleverly choose a subset of the vertices, possibly with weights on those vertices, so that when I make the average on just those values, I get the global average, okay? That's what a graphical design is. So I'm going to define graphical design in a very restrictive way right now, and then later I'll talk about the full version. So let me give you this definition, because this is what's going to be important in the next part of the lecture if you're still here. So I'm going to fix some number of eigenvectors, okay? So I choose some number of eigenvectors to average. It could be the first k, but in principle it could be anything, okay? But usually okay, let's just pick them. Then, so this is this capital phi, and then a graphical design. So a phi graphical design on my graph, of course, on G, is a subset, is some subset which I'll call D, which is inside the vertex set. Typically, we want a proper subset such that it has the property that when I look at the global average of an eigenfunction inside this phi set. So for every phi inside the capital phi, when I look at, this is the global average of the function on the whole graph, okay? This must be the same as the average on just the values on D, okay? So this must be the same as 1 over the size of D times the sum of the global average, let's call it W, such that W is in D. This is what I'm looking for. Should I write above? For all phi in capital Phi. For all phi in the set that I chose to average, okay? So imagine just take the first k eigenvectors, for example, that could be our capital Phi. That's the kind we usually want. So in fact, yeah, so you could just imagine that phi is just the first k eigenvectors, phi 1 through phi k. And what I would like for this set to achieve is that when I compute the global average of the function phi on the whole graph is the same thing as just summing up the values of this function phi on the design or the subset of vertices and then dividing by the total number, okay? So I want global average to be the same as the average on a subset, yeah.
So when you take the average, that's basically the dot product with phi 1.
Yeah, exactly. It's the dot product.
The first few, everything is orthogonal. The average is the rest of the energy.
You're ahead of the game, yes. That's right. Okay. So for so as long as phi 1 is not here, so for phi 1 it's not true. The average of phi 1 is not 0, but all of these other ones are 0, that's correct. So all of these other ones are just, this is the same thing as 1 transpose phi, and this is equal to 0 if phi is not equal to phi 1, okay? So that is the global average. I should have written it the other way, right? The global average, on the other side it's 0. Okay, let me write it on top. So for all phi not equal to phi 1, I will get that the global average, V in V, is 0, okay? So for the eigenvectors, it's true that the global average is 0, okay? All right, so I'm looking for a subset of the vertices that can do this, okay? So I fix a collection of eigenvectors, and then what I want is a subset of vertices that has the property that the global average of every eigenvector that I picked is the same as the average on this collection D, okay? So this collection D, hopefully we want it to be small, and we want the average on that collection to be the same as the global average. Is that okay? On phi 1, we're going to essentially ignore phi 1 for a while because basically every collection of vertices can average phi 1 up to scale, so just ignore it. It's the others that are important, okay? Okay, so that's the picture, and let's do a very simple example. So this example is you take a tetrahedron and you just chop off its 4 corners and then look at the graph that you get, okay? So let me try to draw it. So this one will be like this, okay? And then here there'll be a vertex, and then from here I will get, and then here we'll have a line, and then, okay. So again, we can look at some pictures if we, and then this, okay. So this is really a tetrahedron with its 4 corners chopped off, and then you're taking the graph of the polytope that you get, okay? So this is a graph with 12 vertices. So in this example, V is equal, the cardinality of V is 12. And therefore, there are 12 eigenvectors altogether. And it turns out that if you just take this vertex, this vertex, this vertex, and this vertex, these 4 vertices together can average all 11 eigenvectors except the last one, okay? So this is a D, this is an example of a D, in red, and this D can average 11 of the 12 eigenvectors. Okay, so these can be pretty small. You can have a tiny collection of vertices that can actually average a ton of eigenvectors. So if I'm sampling, blood pressure on this graph, I only need to look at the values that are sitting on the red vertices. I don't need to know the values everywhere in the graph. Okay, that's just a small example, but you see that. Everybody okay with the definition? Okay, a little bit later I will tell you that you're also allowed to put weights here, so you can make a weighted average. But for just now, let's just assume that this is my definition. Okay, global average is the same thing as average over D. Okay, no weights. Okay, so this is the idea. Yes, there's a lot of stuff coming up. Yes. Not for this polytope, but another polytope. Yeah, there is a way to think of it in terms of polytopes. I'll try to summarize it. Yeah, that's right. Sorry? It's the whole graph. There's no proper subset that can average everything. Do you agree? Because if there was, then there will be some, okay, you need weights to fully get that. But if there was a weighted, you also allow weights, then if this was possible for some W that's non-negative. So here I'm choosing my W to be a 0, 1 vector, but I'm allowed to put weights, which I will mention in a minute. So if you do this, then this implies that W is in the span of the all ones. Do you agree? This has to be a span, lambda's bad, C times the all ones. Because W is now orthogonal to phi2 to phi n, so it must be parallel to all ones, or it's like that, right? So then this happens, and if that happens, you see that its support is its support is all of n, right? You have to put a weight on everything, so there is no proper subset, right? Because if W is a multiple of 1, that means there is a weight on every single vertex. W1 is the weight on one, W2 is the weight on the other, and so on. So there's no proper subset that can average all eigenvectors, okay? So you should be willing to leave out at least one if you want to do this. Otherwise, you might as well look at everybody's blood pressure, okay? So that's the game. Okay, so where did this come from, right? So the motivation was, this definition is due to Steinerberger. And as I said, he's an analyst, and he was motivated by the notion of spherical designs, okay? So what is a spherical design? So in a spherical design, you want to integrate functions on the sphere. So you have a function on the sphere, SD minus 1 to the reals, let's say, and I want to integrate this function over the sphere. So I want to look at f dx, and here you put the volume of the sphere or whatever, d minus 1. So you want to know the global average of a function on the sphere, and this is like a very classical result maybe, that you can choose special points on the sphere and just do a average of the function value on those points, okay? So what functions do you average on the sphere? So the correct functions to average are spherical harmonics, which are the same thing as, if in a way they're the same as polynomials as you increase the degree, okay? Homogeneous polynomials as you increase the degree. So of course, if I'm putting a function on S d minus 1, that means my functions have d variables, so these are homogeneous polynomials of degree 1, degree 2, degree 3, and so on. So I'm trying to average polynomials of as high a degree as I can by using just a few points on the sphere, okay? So for example, if you inscribe an icosahedron inside the sphere, okay, so put an icosahedron, okay, this is where we need the computer, but imagine there's an icosahedron sitting inside the sphere, okay, which I'm going to draw with a triangle. This is an icosahedron. So icosahedron has 12 corners, so inscribe an icosahedron inside the sphere, and then the vertices of that icosahedron will be able to integrate all homogeneous polynomials up to degree 5, okay, in the case of three-dimensional sphere. So when d is equal to 3. So the corners of the icosahedron will do it, okay? So this is very much in the vein of, so that's exactly the type of thing we are now trying to do on a graph. So I want to average something over a whole space. I just want to find a collection of points where I can just look at the value there and just sum up those values, and that's going to be the global average, okay? This is also what people do in numerical integration, right? So if you want to integrate a function on an interval, you don't do it continuously. The computer is going to discretize the domain and then just look at the function value over those points and sum it up and so on, right? So for example, we have Simpson's rule, which we discussed in the Gyan course. So this one will tell you that if I want to integrate a univariate function from a to b, f dx, this is the same thing as b minus a over 2 times, I have to take the function value at a, I have to take the function value at b, and then I also have to take the function value at the midpoint. But I also have to put some weights here. There's a weight here that you have to add, okay, which I don't exactly remember. So 4, yeah, okay. There was a 6 somewhere, right? I don't remember where. Is this divided by 6? This was a 6, okay. Something like that. Probably. There are many other configurations too, but basically there are these Platonic solids that seem to live inside the two-dimensional sphere that seems to do the integration right.
Is it also 5 for dot equation?
I think so, yeah. So those are dual, right? Dual polytopes, yes, correct. I think so. So there's a lot of literature on this. People are interested in finding these points on spheres or other manifolds, even tori. That's where Steineberger came from. He was trying to integrate on manifolds, and then he decided, oh, why can't we do this on a graph? So this is the definition. The question is which functions? And in the case of the sphere, I told you they're spherical harmonics. Spherical harmonics are exactly the eigenfunctions of the Laplace operator on a continuous object. So in the graph, we pass to the Laplace matrix and look at its eigenvectors. Okay, so it seems very natural that you go from one to the other. Okay, so then this was the motivation, and I'll show you several other uses of this after we have made some further comments. Is this okay? Everybody got the idea? Okay. All right, so this is what a design is. Okay, so let me first of all make a few comments. Maybe we'll make the comment here. So first of all, I want to say that you can make this definition more robust by allowing weights, like in Simpson's rule. So in Simpson's rule, there are weights on the 3 values that you compute. Whereas in spherical design with the icosahedron, it's uniformly weighted because the sphere is so symmetric, you don't need any weights, okay? But in Simpson's rule, we did need weights. So here is a variation. So you can also have you can have any kind of weights, but the most interesting ones are positive weights. So you can have positively weighted designs. Okay, and now the only difference from the previous definition is that so we take the previous definition all the way here, but the only difference is instead of making the global average equal to just sum of the values on D, we're going to allow weights when you take the values, okay? So what we want is, so D is again subset of V, and now there are also some weights such that the global average 1 over V sum of phi V, V and V. This is the global average. This has to be the same as the sum over some weight. Let's call it D. Okay. So I'm allowed to put a weight here, and this weight is non-negative, and then I am allowed to. Then I take the value of phi V. Okay. So I'm allowed to make a weighted average. I have to choose the weights correctly. So now the data consists of both this set along with these weights. Okay, so it comes with both of them. And notice that these two data together is just captured by the vector A that has A1, A2, A3, A4 as coordinates, right? Because wherever they are 0, we know that part is not in D. All the other things are non-negative. Okay, you can also remove the positively weighted bit. It doesn't have to be non-negative, but that's not so interesting. Yeah. I'm just readjusting so that the division by D is already in here. Okay, you could if you want, but let's assume that the division by D is already captured by the weight. Good? Questions? Is this okay? Everybody got it? Okay. So this is called a weighted design, and then this one, we will call this a uniformly weighted design, the first one. So we will call this type of averaging where there are no weights. This is sometimes called a combinatorial design or a uniformly weighted design. Is that okay? So the most general that I want to discuss is this kind, positively weighted. It subsumes the other one. Okay. All right. So first thing you can ask is, do they exist? Okay. Do they exist? Can you always find, if I fix the collection of eigenvectors over here, are you always going to be able to find some set D contained in V, possibly with weights, so that it'll do this job? And it's really a proper subset. It's not just the whole graph, right? So that's the first question we can ask. And let me give you the first theorem, which is actually chronologically came later. So this theorem is due to Catherine Babaki and myself. This was part of Catherine's thesis. And it says that for every phi that you pick, that is a subset of phi 1 through phi n, okay? So no matter what collection of eigenvectors we pick, there exists, it can even be equal, doesn't matter. So there exists positively weighted designs of cardinality at most the cardinality of the set that you're wishing to average. Okay? So we are wishing to average some collection of eigenvectors, which is this capital phi. So if I choose to average, say, 10 eigenvectors, then I can always find you a positively weighted design where the cardinality of the design, meaning the number of vertices, is at most the number of eigenvectors we wish to average. Okay? So this theorem is actually known in multiple communities. This is also called Chekalov's theorem in some community. So it's simply saying that they always exist, and they always, well, I haven't exactly shown you that they exist, but I'm claiming they exist, and I'm showing you that you can always find something whose cardinality is at most the number of eigenvectors you wish to average. Okay? Okay.
So this, do you not expect about half of this?
It may be lower than this, but in some cases this is tight. Okay? It's Farkas lemma. Yeah, it's Farkas lemma, and it's some polyhedral geometry, and I can explain it in a second. Okay? So yeah, it's not quite column rank, row rank because of the fact that we need non-negativity on the weights. Okay? So we are not just looking for a solution to a linear system of equations, we're looking for a non-negative solution to a linear system of equations. So it's a bit more involved, but not a lot. Okay, so let's see, this goes to 315, right? Okay, so maybe I can show you quickly why this works, if you're interested. And then we can talk about the polytope connection, which is coming next. Okay, all right. Okay, so let me quickly give you the idea of how you prove they exist and how you prove that it has this bound. Okay, it may be much smaller than this, that's true. But in some examples, this is the best you can do. You're guaranteed something at most this size. It can be bigger, that's okay, but we always want the smallest things. So this is what we are guaranteed, okay? So why does this work? So let me quickly give you a proof and then I will show you a different connection to polyhedral geometry. Okay, so let's actually prove this. So proof. Okay, so what are we trying to do? So I'm given this collection of eigenvectors to average. So let's assume that I want to average phi 2 up to phi k. Okay, so this is my collection big phi. And as we discussed briefly, we can always ignore phi 1, which is the all ones, because anything you pick will average phi 1. Okay, phi 1 is not a problem, so just ignore it. So let's try to average the second to the kth eigenvector. Okay. So what are we looking for? We're looking for a solution to phi 2 w equal to 0 up to phi k w equal to 0. W has to be non-negative. Okay? The size of the support is going to come later, but let's first at least show this always has a solution. Okay? All right, so I can repackage this into a matrix. So let's make a matrix whose rows are phi 2 transpose up to phi k transpose. And then what we are trying to say is that, so this system over here is the same thing as u times w is equal to 0, w non-negative, right? So we need to argue that this always has a solution. And then I also need to argue that if there is a solution, there's one with small support, okay? Support at most the number of things we're averaging. Okay, so that's our game. All right, so why is this the case, right? So one way to argue this is to use, so this is sort of linear programming. We're in the world of linear programming. So if you want to know whether a system has a solution or not, you can use this lemma called Farkas lemma that says that either a system Ax equal b, x non-negative has a solution, or there is a y that does something, something. Okay, so let me write Farkas lemma. So we'll put it here. So Farkas lemma is, this is from the 1800s, Hungarian mathematician. So it says that either Ax equal b, x non-negative has a solution, or there exists a y such that y transpose A is non-negative, but y transpose B is negative. Okay? If there's no solution, there must exist such a y. Good?
Only one of these.
And it's a exclusive or. So the two cannot happen at the same time. Okay? You can quickly check it can't, right? Because if you do y, if they both exist, then y transpose Ax, let's compute this. So this will be B, so this will be on the one hand y transpose B, which is supposed to be negative, but on the other hand, what do we have? Yeah, this is non-negative and this is non-negative, so you also have that this is greater equal to 0. Okay, contradiction. So they can't exist together, so it's either one or the other. So it's a certificate, the y is like a certificate that this first system doesn't have a solution. So it's great, right? If you want to convince someone that some million by million system over here doesn't have a solution, you just have to produce a y that's super easy to check. You just have to do y transpose A, check if it's not negative, y transpose B, is it negative, boom, done, okay? So this is a very nice way to certify things, and this is sort of the spirit in which linear programming is in NP, right? Because it's hard maybe to, I mean, it takes some work to find an LP solution, like a linear programming optimal solution. Of course, we know it's polynomial time due to fancy methods, but it's very easy to certify that the optimum you have is actually optimal, okay? It's not this lemma, but there's some using linear programming duality, but this is really the foundation of linear programming, Farkas lemma, okay? This one lemma. Okay, so we're going to use that lemma. And so, okay, we're trying to show that this this has a solution. We want to argue that this has a solution, okay? So if this doesn't have a solution, then there will be a y like this, right? This exactly looks like the ax equal b, x non-negative. So if this doesn't have a solution, there is a y that does something, okay? So I will get that, so this has no solution, implies there exists a y such that y transpose times u is made up of phi2 transpose up to phi k transpose. This will be non-negative according to Farkas, but y transpose times, I'm going to make this a little bit more interesting. Let's not go here quite yet. Okay, sorry. Okay, I'm going to make this a little bit more interesting. Okay. So let's set up u not exactly like this, but I'm also going to include the phi1. So phi1 is all ones, and then phi2 transpose up to phi k transpose. Okay. So let's make u this. I just added one more row, which is the all ones row. And then what I need to argue is that when I multiply this u there is some solution to uw equal to 0 in the second through the kth position. But in the top position, it's going to be what? This is like 1, 1, 1, 1, 1, 1. So when I multiply it with w, which is non-negative, I will get something positive, which I can scale down to just a 1, right? Because if I have a solution and I positively scale it, it's still a solution. So we can assume that this is 1, okay? So let's try to argue that this has a solution. Good. It's the same as showing the other thing had a solution. Okay, so suppose this has no solution. So this is just E1. So this has no solution implies there exists a y by Farkas lemma such that y transpose times phi1 transpose, phi2 transpose, phi k transpose is non-negative, and y transpose times E1, which is the right hand side, which is the same thing as y1, is negative. Do you agree? Okay, so I'm trying to show this system has a solution. If it doesn't have a solution, then by Farkas lemma, there is a y that will multiply the matrix on the left to give you something non-negative, and it will dot with the E1, which is the right hand side, to give you something negative. Good? This will happen. Okay, so let's unravel this. So what is this? This is a linear combination of the rows of this matrix. So I will have that y1 phi1 transpose plus y2 phi2 transpose plus up to yk phi k transpose is greater equal to 0. So this is a row vector, right? These phi1 transposes and so on are rows. So this is some row vector, and that's greater equal to 0. And I have this. I have that y1 is negative. So without a loss of generality, I can assume that y1 is minus 1. Do you agree? Because again, positively scaling things doesn't change the fact that there is a solution. So let's assume y1 is minus 1. So that means this is a minus 1. Okay? So this will happen by Farkas lemma. Good? Okay, so now let's just let's take the dot product of this with phi1, okay? So let's just take the whole thing and let's multiply it on the other side with phi1. So phi1 transpose is a row vector, so this part will become minus the norm of phi1 square, which is something positive. But then after that, phi2 transpose phi1 is 0 and so on, so the rest is just 0. So plus 0 plus 0 will be greater equal to 0. Okay? So we can ignore the zeros, and I will get that something strictly negative, because the norm of phi1 cannot be 0. So something strictly negative is greater equal to 0, contradiction. Okay? So this has to have a solution, which is the existence of a design. Okay? So that shows you that designs always exist. So no matter what phi1 through phi n you pick, or whatever, no matter what collection we pick here, there will always be a positively weighted design, okay? So why is it of small size? That's the only part that's left, right? We want to argue that it's small size. So to do that, we do a little bit of polyhedral geometry. So we just argued that this system down here has a solution. So let's again just look at that system a little bit carefully. So what that system is saying is that, so what we argued that U times W is equal to E1, W non-negative has a solution. Okay? But what is this, right? So this means I'm taking a non-negative combination of the columns of the U matrix. I'm doing the first column of U times W1 plus second column times W2 and so on, but they're non-negative combinations. So let's put the columns of U somewhere. So let's say these are the columns of U. These are the columns of U. I'm saying W is a non-negative, E1 is a non-negative combination of the columns, but non-negative combinations of some vectors is the cone spanned by those vectors, okay? So really, I'm just looking at the cone spanned by those vectors. Let's put more vectors. And I'm just taking the cone of those vectors over the origin. This is the set of everything that looks like UW, W non-negative, okay? And we're claiming that we know that E1 is in there. So we proved it. We proved that E1 is in there. So E1 is sticking out. This is E1, okay? So now you may know this already. So if it sits in a cone, so let's look at the top picture. So the top picture is like this. I have some polyhedral cone that's given by the columns of U. And here is E1. It's sitting out. It's sticking out. This is E1, okay? Then you may know that you can always put it in a subcone. There is always a way to find a subcone of the big cone that uses only dimension many extreme rays, okay? So this cone has n extreme rays, right? Because there are n columns to the U matrix, but the dimension of this cone is small. The dimension of the cone is only the number of rows in this matrix. So the number of rows is k. This is a k by n matrix. N can be large, k is small. So what's happening is there are n things in these extreme rays. There are n things, but the dimension is only k. Okay, so there's always a k-dimensional subcone in which E1 also lies. Is that okay? This is called Carathéodory's theorem for cones. That you can always, this is also true in a polytope, right? If you have a point in a polytope, you can always find a sub-polytope, which is a simplex that contains your point. There are many ways to do that. Yeah.
I was thinking of k versus k plus 1. Because in the polytope it's k plus 1.
Yeah, yeah. That's right. This is sort of the homogeneous version of a polytope, right? Yeah. So if you cone over a polytope, it's the same thing. But big cones are nice, so we just need the dimension. Exactly. And notice this triangle is not unique, right? I could have also chosen this triangle. That would have also done the job. No matter which one, there is always one. There's probably many such that it sits in that subcone, right? So that means I can write E1 not as a non-negative combination of everything. Yes, I could. But I could just write it as a non-negative combination of these k things. That's where the support bound is coming from, okay? So there is something of size at most, the cardinality of the set that you're trying to average. Good? Okay, now this is very important that this happens for positively weighted designs. If you don't allow weights like this, it's actually highly non-trivial to argue that there is something of this small support. And it's generally not true, okay? But there are some big results like for, which I'll talk about maybe in the next section, but you may have seen these results of Kuperberg, Lovett, Peled, and so on, that say that there are orthogonal arrays of cardinality at most, that thing that I want over there, and so on. So there are like these powerful results that are very, very recent that is essentially saying there are also these unweighted designs of low support in special cases, okay? But that's actually a non-trivial theorem. Most of those theorems are just probabilistic. There's no construction of the actual design. It's just saying there exists because of some very fancy Fourier analysis attached to probability, attached to a bunch of other things, okay? There's also...
In terms of the nature of the support,
it's
where is the hypothesis based?
on the graph. It's not quite even graph. They don't even work in the world of graphs. So, so I'll just say the result to you. Maybe it makes sense or not. So there are these things called orthogonal arrays, which are collections of 0, 1 vectors, such that if you restrict to it, nothing to do with graphs, such that if you restrict to like t coordinates, you will see all the vertices of the t-dimensional cube appear equally many times. Okay, these are called orthogonal arrays. And then people wanted to know whether there are orthogonal arrays of cardinality at most something. Okay, so in the next section, if you're here, I'll show you that those are all graphical designs. So there is a way to put a big umbrella on things like orthogonal arrays, combinatorial block designs, T-wise permutations coming from the symmetric group, all kinds of things. So highly combinatorial objects appear as graphical designs on special graphs. Okay, so they'll always have that bound, but the bound that the combinatorialists care about is this bound, because they don't like weights, right? Combinatorialists don't like weights. They want to put 0, 1 over here, and they want to say that even if you impose this, that bound is true. Okay, that's non-trivial. So the existence of combinatorial designs like that is due to Peter Kivash. It's like a 2014 result. Again, these are very difficult papers, okay? And again, oftentimes there's not a construction, but an existence proof. So that's a harder problem. But my statement there is about positively weighted designs, okay? Okay, so let me tell you one more result, and then I'll show you some applications, and then we'll stop for the first part. Actually, okay. Actually, let me show you an application, and if we have time, we'll come back to the polytope result. Okay, application 1 to random walks. Okay, so let's do an application to random walks. Okay, so here's a theorem that we proved that I will write down, and then I'll comment on it based on what was known before. So this says that for L, for 1 less or equal to L less or equal to n minus 1, there exists a probability measure mu0 supported on at most L vertices This is random walks and graphs in the graph, okay? So it's supported on at most L vertices in V such that when you look at the sequence of probability measures, so that remember how the probability measure advances. So if you want to know if you have an initial probability measure, is our random walks familiar to people? Should I say what is happening? Okay, so what's a random walk on a graph? You start in one vertex typically, and uniformly randomly you choose a neighbor to walk to, okay? Then uniformly randomly you chose another neighbor to walk to. That's a random walk that starts in one vertex, okay? And then as you're advancing, you start with some measure mu0, which is just a Dirac measure. It has all its mass on the vertex that I'm standing at, 0 everywhere else, okay? And then in the next step, we'd like to know what's the probability that I'm at any vertex, and that's given by a recurrence relation. So if I want to know the probability that you're at time t plus 1, if I want to know the measure, this is the probability of standing at vertex 1, standing at vertex 2, etc. This is a vector. This is given by, let's assume it's a regular graph. So it's given by this adjacency matrix divided by the degree times the previous probability measure, okay? So there is a recurrence relation that tells you how the probability measure advances as time goes on, okay? So here I'm using this, so mu t of A is the probability that the walk is at A at time t. Okay, that's what it is, okay? All right, so that is that. And there's a classical result that says that if you want to look at so even in most graphs, eventually the measure will become uniform. The probability of being at any vertex becomes the same after a while, okay? So you walk, this measure is spreading. Eventually it just converges to the uniform measure. You have equal probability of being on any vertex, okay? That's called the uniform measure. So the difference at any time t, mu t minus this is the uniform measure, the measure that puts 1 over n on every vertex. So this norm square, if I want to know how close am I to the uniform measure, this is bounded above. So normally what we know is that, okay, so what our theorem says is that this is bounded above by the L plus first eigenvalue to the 2t, where Li are the eigenvalues, not of the Laplacian now, but of this matrix, of the 1 over dA matrix, okay? So it's a normalized adjacency matrix, and it's saying that the convergence rate is controlled by the L plus first eigenvalue, okay? Why is this significant? So for this matrix, what's happening is for this matrix, the eigenvalues they're going to start at 1, okay? So 1 is the biggest eigenvalue you can have. This is a Markov matrix. And the smallest eigenvalue you can have cannot be lower than -1. Okay, so the spectrum is between 1 and -1. So this one is going to be the top eigenvalue. This is lambda 1. Okay, then the next one is usually counted in terms of absolute values. So the next one, if this is lambda 1, the next one could be here. This is lambda 2. Okay, this is how the eigenvalues of the walk matrix, this is called the walk matrix. This is recorded. So this is this, then maybe lambda 3 is here, maybe lambda 4 is here, and so on. So at the end, so lambda L is maybe here, okay? So as L increases, the lambdas are getting closer and closer to the origin. So what we're claiming is that for any L you pick, I can find you a measure that is supported on at most L vertices, where the convergence rate to the uniform measure is controlled by lambda L plus 1, can be very small, okay? What's known is that this is controlled, if you start with the uniform measure, so known was that if your uniform measure is Dirac, so this measure is initial measure, sorry. This initial measure is just 1 on vertex 1 and 0 elsewhere. Yeah, is delta. That is a Dirac measure on some vertex. Then the thing you got to put here is lambda 2 to the 2t. Okay, this is what was known. So this quantity over here is less or equal to that. This is the folklore result for random walks. Okay, convergence is controlled by lambda 2. And lambda 2 is the second largest eigenvalue in absolute value. Can be pretty big, right? But we're saying, what? It's squared. It's squared, right? So you could have a modulus, but it's squared anyway. So don't worry, okay? Right. Yeah, assume it's D regular. You can get rid of that assumption if you like, but I'd just say it for D regular. Good? Okay, so we're saying that instead of starting on a Dirac measure where you put all your weight on one vertex when you start, if you're willing to even start your measure with 2 vertices as its support, then the convergence rate is controlled by lambda 3, which may be a lot smaller than lambda 2. Okay? If you're willing to start on L vertices, if you have 5 people walking on your graph, you will converge to the uniform measure with rate controlled by lambda 6, which is even much, much smaller than lambda 2. Okay? So this is saying there is a choice of measure that can drastically increase the convergence rate. And what are these measures? They're exactly these designs, okay? They're exactly these designs. So that's a first application of these measures, of designs. Any questions? Is okay? All right, okay. So, yeah. And now let me show you. So another application is to sampling. So you can, as I said with the example from the beginning with medical data or whatever, you can use this to sample a graph. And we have some results on this too that says that if your function is mostly a function of some low eigenvectors and maybe has small coefficients on some other eigenvectors, then you can control the sampling error quite well, okay? So maybe I don't actually fully write that result, but let me just at least claim that there is application to sampling. Okay, so to sampling. Okay, so those are two applications, but let me finish the talk right now with this polyhedral connection. Okay, so the polyhedral connection is the following. So I won't prove anything, it takes a long time to prove it, but I'm just going to show you a recipe that shows you that all designs, after you've fixed which ones to average, are organized on the faces of a polytope. Okay, so there is a beautiful polytope that you can construct, and on its faces sit all the designs that you would care about. Okay, and the facets, which are the codimension 1 faces, carry the smallest designs. Then the next smaller faces contain bigger designs and bigger designs. So it's an inverse relationship. The bigger the face, the smaller the design, and you go downwards like that. Okay, that's the result. So here's a recipe. It's everything. So if you go to the interior, it's the full, you have to take the design to be all the vertices. But if you take a vertex, better. If you take a facet, best. Okay, so you don't need, the facets carry the minimal designs, the ones that have this bound. Okay. Okay, so what's the recipe? So I'm going to give you a recipe here. So I'm going to take, these are all the eigenvectors of the Laplacian. So let's say phi1, phi2, up to some phi k, and then up to phi n. Okay, so these are all the eigenvectors. This is an n by n matrix, right? And suppose we wish to average everything from here to here. So I want to average this part. Okay, so I want to average this part. Remember, we always leave out the all ones because it's averaged by everything, so don't worry about it, okay? So I want to average this part. So let me focus on the complementary part. Let's focus on this piece and this piece. Okay? And now I'm going to bring those two together. So I'm going to create a matrix that has just all the pink stuff. And this one will have, it'll have the first row will be a bunch of ones. And then after that, it'll be some other, these guys. Okay? So I get a matrix like this. Okay. Now I'm going to do something. I'm going to take the columns of this matrix. Okay. So let's take the columns of this matrix. So it has many more columns than rows. Do you agree? Because I plucked it out of an n by n matrix. I take the columns of that matrix. And then I'm going to, so let's give this thing a name. So let's say down here I have, no, not V1. What's another letter? Maybe C1, C2, C3, up to Cn. Okay, these are the columns. So these are columns of this part. So remember, the rows are the eigenvectors, but I'm passing to columns, which sounds really weird, but this is what we got to do. Okay, so take the columns and then construct a polytope that is the convex hull of these columns with the one on top. Okay, so I'll get a polytope. Okay, I don't know, something like that. Trying to draw something three-dimensional. Maybe I should have kept it two-dimensional. Okay, so I get a polytope, and the claim is that D, so the theorem, which is due to, it's in the same paper as that one, so Babeke-Thomas, is that D is a phi design. D is a positively weighted, so I'm averaging these guys, so I'll make it yellow. So it is a phi design. If and only if the columns correspond, the columns 1, Ci, such that I is not in D, okay? Not in, we have to take the complement of D. So these things lie on a face of P. That's the result, okay? Okay, so let me just parse this. So what this is saying is if D is a positively weighted design, that means, remember, there's also a weight attached to it, but don't worry about it. Just let's look at the vertices that are in the design. Then that happens if and only if, when I convexify this complementary set of eigenvectors on their columns, okay, I get a polytope, and D is a design if and only if the complement of D corresponds exactly to the points that live on a face of the polytope, okay? So now let's just work with this a bit. So if I want a really small design, I want lots of things to lie on a face, right? The biggest faces are facets, which are the codimension 1 faces of the polytope, the big flat sides. So on those big flat sides, a lot of these columns should lie. If they do, then the complement is a very, very small design, okay? So the facets of this polytope carry the smallest designs in their complement. And as the faces become smaller and smaller, there are less and less things lying on them. 1 Ci, less and less of those lie on those faces. So the designs become bigger and bigger, okay? So that is the idea. And yeah, so this also gives back this bound. You can reconstruct this bound because every facet is at least a simplex. So you know that every facet has at least, you know, D many, if D is the dimension of the polytope, D many vertices. So the complement cannot exceed n minus D. That's the same as this bound, okay? So that gives a bound. It shows the existence and all these kinds of things. And we have some pictures, so maybe we could show them. Do we have time? Or should we do it at the beginning? Beginning of the next one? Yeah, either way. We have 5 minutes. Yeah, let's quickly look at a picture and then we'll stop. Here's the truncated tetrahedral graph again. And I want to average all these blue vectors. Okay, this is what was yellow before. I want to average all these. So the recipe is take the rest, take the pink stuff, okay? So I pull out the pink stuff and I'm going to convexify their columns. So there's this row of ones on top, but then I'm really convexifying these columns down here, okay? So if I just pull that out, then you see, I just pulled that piece out, okay? So that's the row of ones and then this bottom row. So if you look carefully at those, it looks like it's a 12 gon, right? I have 12 columns in two-dimensional space, essentially two-dimensional space because you can ignore the ones. But then the columns are doubled up, like all the yellow columns are the same, all the blues are the same, all the pinks are the same, right? So really when you convexify, you just get a triangle. And you have to remember which labels went with which vertex, okay? So for example, all the pink guys, which are 1, 1, 0, they are at this point, okay? All the yellow guys are this point, all the blue things are this point. That's what all it means. So now what the theorem is saying that if you pick a facet, like this facet, then the columns that lie on this facet are the ones with index 1, 6, 7, 11, 3, 4, 9, 12. So the complement, which is 2, 5, 8, 10, is a design that can average all those blue vectors, okay? So here's the design, this design I showed you at the beginning. This is the design that you get. It can average all of those 12 vectors. All of the blue vectors. So that's not 12, 9, right? 11? Including the all ones, yeah, including the all ones, that's right. So it can average all of them. So the designs are sitting on the faces of this triangle, okay? Let's do something slightly harder. This is slightly harder, Peterson graph. So in this graph, there are 10 vertices, so 10 eigenvectors. And suppose I choose to average everything except the ones you see here, okay? So here you see 5 eigenvectors plus the all ones. So I want to average 4 that are missing, and these are the remaining ones, okay? So if you convexify these columns, it looks complex. It looks like something with 10 vertices possibly in 5-dimensional space. But again, there is a doubling of columns. If you look, no, there is no doubling. There is no doubling, okay. So if you convexify the 10 columns, then you get a 5-dimensional polytope, and this is its face vector, which means it has 10 vertices, 45 edges, 90 2-dimensional faces, 75 3-dimensional, and 22 4-dimensional faces, facets, okay? So the facets are the most interesting. They carry the smallest designs, and these facets come in 2 types up to group action. So there are 12 simplicial ones, which means that they have 5 vertices on them, right? Simplex in 4 dimensions is a facet. This is a 5-dimensional polytope, but a facet is 4-dimensional, so that has 5 vertices. And so that means the complement is also 5. They correspond to 5 cardinality designs. But then the other class of facets come with 6 vertices, so their complement is 4. Okay? So you do need some software to deal with arbitrary graphs, but here we could use some group action to cut down how many types we have. Okay, so this is the type of example, and then maybe I'll just show you the eigenvectors that I promised, but they're not here. They're in a different day. Okay, so this is what I mean by eigenvectors become less and less smooth. Okay, so this is the United States graph where edges connect neighboring states. Okay, and this is the walk matrix whose eigenvectors we're looking at. So it's not a regular graph, but we can still compute its eigenvectors. This is the first eigenvector of the walk matrix, meaning the one with the maximum absolute value. You see that when you go across from one vertex to an adjacent one, the color doesn't change too much. It's pretty smooth, right, the variation. The second eigenvector looks like this. Also, you just have to look between adjacent things, okay? Don't look all over, so it doesn't change too much. But then you see the 11th eigenvector. It oscillates quite a bit. And so this is what I mean by you can average like a smooth function, like for example rainfall, by just looking in the span of the low eigenvectors, the low things corresponding to low eigenvalues, and therefore we only care to average those. If you want to average f, it's enough to average the eigenvectors that you can write it as a combination of. Okay, so that's really the philosophy. Were used here? So this one, what do you mean? So this one has like this is probably just the 48 states. So there are 48 eigenvectors altogether. Oh, for the rainfall? Oh, I don't know. It's just for inspiration. Yeah. It's just okay, thanks. Yeah, I don't know. We didn't try to average this. All right. Any other questions? Oh, you want to say? Yeah, happy to take questions. This is the end of the first part. In the second part, I'll actually talk about graphical designs on cubes, which are these orthogonal arrays and so on, and SN and something else. Yeah, cubes mostly.